Okay, good morning, everyone. Today we have a relatively short lecture. The reason for that is because in the beginning of this lecture, I'm going to spend probably use 10 minutes or 10 to 15 minutes to talk about the second assignment. So I was wondering if all of you have already looked at the second assignment specifications? Yes? Okay, good. So the second assignment, as you can see from the specification, the first one was an individual assignment, right? The second one is a group assignment, right? So you are strongly encouraged to work in pairs, right? So one common question in the past was, can I work in a group of 3 or more? The answer is no, because of the working-node, right? So this is basically our working-node. It's an assignment designed for ideally 2 students, a group of 2. But some, may want to do the assignment still do the assignment by yourself because of different reasons. For example, job commitment. There are quite a few of you who are working full-time and study part-time, so it's very easy. It's not easy to find a common time to meet or to do assignment with a partner, so which is reasonable. So if you are keen to do the assignment by yourself, that's okay. You don't need to get the permission from a tutor or from me, so you can just do that, right? No problem. But the criteria, the requirement and the criteria used for mark the individual assignment, as I said in the specification, will be exactly the same. All right? This is one thing I want to emphasize, want to talk about. Another one is, if you work in a group, I want you, as I also mentioned very clearly in the assignment specification, I want both members to involve, to contribute all aspects of the assignment. So for example, one of the ADT that you need to develop is a movie, another one is a movie collection. I want you to work closely together on all of them, rather than split the task into 2, and you do one part, I do the other, the other part, and then finally put them together. So this is not good, because in this way, if you're doing assignment like this, you probably, because the assignment to me is, the assignment is assessment. That's for true. And the assignment is also, I think, is an activity through which you can learn something, right? So, but if you only work on one particular area, you probably miss something, right? So this is the reason. So that's why I said number 1, the 2 members needed to make an equal contribution to the assignment. Yes?
So you said like you want to actually work on it together. What about the idea of actually you developing your own separate component, but then once it's developed, you refactor the other person's component?
This is a good idea. This is a good idea. But in this way, so eventually both parties will evolve all the component, right? It still evolve all the component, contribute to all the component of your assignment. Yes, that's another way. But eventually, you're still working on everybody working on every component of the assignment, right? So that's another way. This is okay. This is not a problem. Yeah. Any other questions about group assignment? Okay. So roughly, you should make a rough equal contribution to the assignment, and therefore the two members in the group will receive the same mark for their assignment. All right. So this I should make it very clear. And of course, I will talk about later on in the statement of the completeness. All right. So for this one, I believe all of you have already looked at the specification already. So the background, what's the background, what's the rationale for this assignment, right? So this is it's a very, I think should be very clear. So basically for this assignment, as the title of the assignment is to develop our application for video store management system. So video store, there, in that video store, there are number of DVDs, actually movie DVDs, right? One movie may have multiple DVD, multiple copies. So if I want 3 copies of the same movie, right? We have initially we will have 3 copies of that one particular movie. Later on, you say, oh, there are a lot of customers who want to watch that DVD. So maybe the owner or maybe they want to, they can purchase more. For example, purchase another additional 2 copies of the same DVD, right? This is one possibility. Yes.
Just as simple as that, adding 2 copies, or do you want us to add a barcode for the additional?
Okay. Yeah. This is your implementation details, which I don't care. For some of you, that's implementation details. Some of you may want to use something like a barcode to uniquely identify or to distinguish the multiple copies of the same DVD. But you don't have to do that. This is really depending on your implementation details. If you find, okay, by doing that, it can get some benefits, it can be very convenient to achieve, implement some functionality, just do that, no problem. This is just the internal. So this is something that we cannot observe from outside of the system. This is something inside. So this is totally up to you. You can use a barcode, you can use an integer, or use a string, whatever, to uniquely to represent the DVD, so that you can distinguish multiple DVDs of the same movie. But again, you don't have to do that. So totally up to you, right? And are there any questions about that? Okay. So basically, another question, there are some very specific requirements for the assignment. So this is something that I want to emphasize right now. I sent an email talking about the requirement, the specific requirement for movie collection and customer collections. Is it customer collection or not? Customer collections, right? Because in the specification I said, for movie collection, you must use a binary search tree. Where for customer collection, you have to use a vector, right? So this is some, as I explained in my email. Did you see my email about this clarification for this one? Okay, good, that's good. So why I say, why I can't use other data structure, which I think is pretty more suitable? Maybe not. So for example, if you use a map, the fundamental data structure is still binary search tree, right, in the practical. So you use this movie collection, either use some data structure to store the movie or DVDs, and you can directly use binary search tree, or you can use a map, which actually use a binary search tree. So what's the point to introduce one level of abstractions in the middle? Anyway, this is not the most important point. The most important point is, as I mentioned in my email, the assignment is assessment. So in assessment, I want to check your guys' knowledge and skills for this particular data structure. This is the major reason. So you have to use binary search tree for movie collection. You have to use a vector for customer collection. For the vector, as I also mentioned in the specification, you can develop a vector from scratch by yourself if you want. Or alternatively, you can use the vector template coming with the STL standard template library. So either is okay, I don't care. So as long as you use a vector, perfectly fine. All right. So for the specific data structure, you have to follow. Otherwise, you may get some, actually probably got a lot of penalty, pretty harsh penalty for that. For example, for the implementation, you probably get a 0 if you use a wrong data structure. Why? Because you use a different data structure, the implementation would be totally different, right? You can, for example, first one, if you want to make the implementation a little bit easier, you can simply use a vector for, for movie collections, right? You can do that, but this is not what I wanted. So I want to, to access your guys' skills, the competitors, or, in that particular, for this particular topic, particular area. That's why. Okay, and for this one, I think the functionality requirements for this assignment should be very clear. So basically, you have you initially have a main menu. In the main menu, basically you should do the authentication. So if you need to put a username and a password. So if you are a staff member, so there are two different members, users, I should say. One is the staff member, another one is the normal registered users, right? If you're a staff member, then there are as I said, there are two subscripts. For example, when they verify you, if you're a staff member, then the system will bring up a sub-menu, which is which has a list of functionality for the staff members. For example, the staff member can add a DVD of a new movie to the system. The system should allow the staff member to add the DVDs of an existing movie and so on and so forth. Can register a new customer with the system and so on and so forth. If the user is not a customer, or if the user is just a customer, and then you should bring up another menu, which is the sub-menu for the customers. So, for example, as a customer, a different menu, right? Bring different menu for different type of users. So, for example, for the registered users, for example, they can browse the DVD, the movies by title, and they can display the information about a particular movie that they are interested in, and they can rent a DVD, can return a DVD, and also can do something else. So it's a list over there, right? So this is basically the function for the functional requirement. So if there are any functional requirement that you are not very clear, please feel free to send me a quick email. And if the question is very common, then I probably, when I reply your email, I'll probably also copy to the class email list. So this is what I can do. For this one, another thing I would like to mention right now is for the submission, right? For this one, you have to use code blocks. So last time in the assignment 1, so even I said very clearly in the assignment specification, I said when you submit assignment, you need to submit a project, a code block project, the whole project, rather than just some programs, .cpp or .h files. But we still got a few students, not many, just probably a couple of students who only submitted the code, the programs, didn't submit the project, right? So and we didn't penalize for that. But in the second assignment, if you only submitted, for example, the .h or .cpp file, most likely the marker will give 0 for the functionality, and then you have to come back to review the functionality with your marker, which is very complicated, right? So I would suggest you must submit a project, a whole project, rather than just the .h, .cpp files, right? This is one thing. And For this one, just keep it simple. You don't have to, actually you should not, let me put it this way, you should not save any information about movie, DVDs, about customers into a file. You don't need to do that for the assignment, all right? So it just make the assignment a little bit easier. So you don't need to save, we don't need any processing storage. Yes?
Can we still do it just for testing? Because I hate having to repeat information.
I see. Sure. Yes, you can do that. Yeah, you can do that, yeah. And of course, you must use a standard C++ library. Okay. If you use any class library, C++ library specific to a particular compiler, it's not a standard, these are not acceptable. All right, you have to use a standard C++. If you wish, you can use any other, any C++ standard libraries, right, if you want, for the assignment. Okay, finally, yes?
Just a quick question.
Sure.
It says here that we can create and use other ADTs.
So say again, we can.
Sorry, it says here in the assignment requirements that you can create and use other abstract data types in addition to like moving completion.
Yeah, if you want, yes.
Yeah, do you have specific limits on how many?
There's no limits. You can have as many as you want, as long as they are make sense. That's perfect. There's a limit. So there are 4 ADTs or classes that you have to create. They are movie collection, customer collection. So this is something like we did in assignment 1. We are use the similar criteria to check the quality of the ADTs. For example, the specification. Did you use right data structure? What about the prototype? The comments, and so on and so forth, and implementing details. So we're using the similar criteria to check your 4 ADT, those 4 ADTs or classes. But if you want to use any other classes, if it makes sense to create another class, that's perfectly fine. You can create as many as you want, doesn't matter, right? But we only, for the ADTs, we only check those 4 ADTs. If you create another one class, like class 1, so we are not check the quality of that class. For, there one category is ADTs against IDT criteria, but we, of course, eventually we still need to check the functionality. And also, there is some overall, for example, the readability, the quality, and so on. So we are still, maybe give you some penalty if it's not done very well done. Give some penalty for that. Not in the category of ADTs, but maybe in some other area. If you're not done, if they are not very done properly, maybe there are some deficiencies. Could be penalized. Yes. This is just a command line. There's no go. Yeah, keep it simple. Yeah. Otherwise, it's a little bit hard to manage. Yeah. So for the tutors, I mean, are there any questions? Okay, submission. Submission. So there's a deadline. There was a guy when the first assignment was due. There was a guy who submitted an assignment actually on, exactly, and actually on. At the one last minute before the how should I explain this to you guys? So you should read it very carefully. So the deadline is before that time. If you submit at that time, then the system still say later submission. Actually, it's happened that there was one guy who submitted just 1 minute before the midnight. And they get a feedback is your submitting was late. So just make sure you guys are aware of that. Another one is this is something that is different from assignment 1. So in addition to the whole project, you also needed to submit another document, which I called the statement of completeness. And also I said very clearly what sort of you should be included in the statement of completeness. For example, you should specify if your system is fully functioning or not. If it's not functioning, which part is not functioning? Have you attempted, any node deficiencies, and so on and so forth. And also, very important, if you work in a group, because for one group, you only need to submit one copy. All right? So if you submitted 2 copies, so one submitted each, and they are marked by 2 markers, then we have to use a lower mark, all right, as a penalty. So basically, you need to submit only 1 copy from each group, all right? So I would like to make it very clear, all right? And also, you can, this submission, multiple submission, resubmission is allowed. You can resubmit as many times as you want, but we will only mark the last one right before deadline. That's the only version that your marker will mark, will grade, right? They will not look at any versions, any submissions at all. All right, so just to make it very clear. Any other question? Yes?
Yeah, sorry, just another question about CRA. I noticed the CRA that we got back in the first assignment.
Right.
It was much more detailed than
I say, I know what I'm talking about. Yes, yes. Actually, we realized that the reason why, so initially when you given the criteria, marking criteria, this is probably is pretty high level, pretty general. There are 2 reasons why we didn't give a detailed marking criteria in the first place. Because it's very dangerous for doing that, because different people may use a different way to implement. So the detail, if you look at some detailed criteria, some detailed criteria may applicable, for other applications. So it's very, very dangerous. So to do that, right? So this is the major reasons of why we don't give your detail criteria. Actually, the detailed criteria should be, actually, I interpret it in a different way, because when the marker mark your assignment, they need to give your guys some written feedback, right? Without those comments, I would say those are some more detailed comments to say what the justification why I take some mark off for this particular criteria, right? This is just, without that, the tutor would have to, type in the comments one by one. So that's why we put some common problems over there. So if these are applicable to you, the tutor simply tick this one off because they didn't do this. So this is the intention. So this is actually, I personally, I interpreted those as not a criteria, but some more detailed feedback and comments. So this is just to use to facilitate the markers' work job. They can do the job a little bit quicker and easier. All right. But of course, what I'm worried about is, again, the definite issue. If we design some detailed criteria, then that's risky. So may not apply to all the assignment. Different people maybe do the assignment differently. Right. So this is the, yeah. Personally, I still want to keep it more general because, as I said, it would be very dangerous if I have more specific. The specific criteria only apply to specific implementation. If anyone uses a slightly different implementation, then they are not applicable. That would be a disaster, dangerous. Yeah. Any other questions about the second assignment? Okay, that's good. If you have any questions about second assignment or clarifications at any stage, please feel free to send me a quick email or to ask me during the lecture or in the beginning of lecture, whenever. Yeah, okay, no problem. So now we move to okay, today we are talking about another type of data structure called hash tables. So this is the agenda, basically, for today's lecture. First of all, I just talk about why we need a hash table. All right. There are a lot of real-world applications where you need to have a very quick very quick traverse and a very quick insertion and deletion, right? So this is one example is, for example, in the driver's license transport, like a Queensland transportation system, there are probably millions of driver's license needed to store in the system, right? So one problem when you develop a system like that, one issue you would have to address is what sort of data structure should I use to store that particular data, all right? So for driver's license, basically, we have each driver, if you look at the driver license, each driver license has a driver license number, right? Which is unique to identify you, and plus some other information, for example, your contact details, your residential address, and so on and so forth, right? All the information. So one problem is, so from time to time, for example, in the placement or in station or maybe in the Queensland transport, from time to time, they need to check, for example, the background of our drivers, giving our driver's license number. They need to find the information very quickly, very, very quickly, right? So by now, what sort of data structure we have learned so far? So we have, for example, we have like an array, we have a vector. So basically, there we said they are list, right? Sort of a list, array and vectors. And we also talk about, we also know there's another type of data structure, which is a binary search tree, which support a more efficient searching or retrieving or something like that, searching, right? But the best of the, but the most efficient data structure. So basically, there are two most efficient that we'll talk about so far. One is sorted array or sorted list. So if it is sorted, we can use a binary search, right? And the computational complexity for binary search is log n. This is one of the most efficient. Another most efficient we have learned so far is binary search tree. So binary search tree, similar, have the same computational complexity, right? Big O of log n, right? But the size, when the size of the program, no matter it's log n or bigger log n, linear search is a log n. Oh, sorry, linear search big O for n, binary search log n, which is quicker, it's better than big O for n, linear search. But the time, the search time, we just use a search as an example. The search time is still in proportion. Let me put it this way. The search time still increase with the size of the problem increase. So for example, if your array is a very, very long array, a sorted array, you do a search, or use a very short array, of course the longer one take a longer time. So generally because of search, why? Because the search space is more, right? So that's why. Now the problem is, we're trying to find, for example, a method, a data structure, which can, for search, insertion, and deletion, basically, we can get the result back. We can finish the operations in constant time, which of course is much, much better than binary search, much, much better than linear search, right? And also, when we say constant time, I mean, when the size of the program increase, the operation time, the computing time will not increase dramatically, pretty much the same, right? That's what we call constant time. So the solution is we can use, so one of the solutions is we can use a hash table, all right? So what is a hash table? So hash table, number one, is a data structure. It's very, very fast in some operations. For example, search, insertion, and deletion. So those are three operations. They are very efficient. They may not be very efficient in some other area, for some other operations, but they are very fast in insertion, deletion, and search. Very close to our constant time or big O of 1. All right. So our hash table store our collection is also a container, but different from other containers. It store some other container, I should say. It store a collection of key value pairs. For the driver's license example, the key is the driver's license number. Right? The value is the other information about the driver, for example, residential address, phone number, and so on and so forth. Right? Typically, the implementation eventually, this is data structure. Eventually, you would have to have a fundamental or physical data structure to hold those key item pairs. All right? And typically, we use array. We use arrays actually to hold the key item pairs. All right? So this is the. And our core technology in hash table data structure is called hashing, okay, which I will talk about, explain to you. What's meant by hashing? So hashing means the basic idea behind the hash table data structure is, so for example, you have a number of key item pairs. So now we are only interested in the key, right? We are not interested in the value. Right. We'll have, for example, have K1, K2, K3, K4, and so on and so forth. Hashing is, rather than use, we check, for example, binary search. If on search, you have to, so how we do search? We use a comparison, right? We compare this, compare that one systematically. So either in binary or linear sequentially, right? But here it's different. We map the key, we hash the key to this. Is we call, as I just said earlier, we need an array to store the key item pairs. Key item pairs, how? Okay, number one is, first of all, we need to work out giving our key item pair, where should I store in this hash table, which is array, in this array, how could I do that? So the solution is for hash table. So for the key, we build, there is another concept called, so we define a function, we call it hash function. So giving a key the hash function, do a little bit very quick, simple calculation to work out address for storing that key item pair. So for example, this is a mapping. For example, if the hash function, if this can map to, for example, use a hash function, which I'm talking about next. So the value is 0, not 0, m minus 1, right? Then we store this corresponding, so the key as K4 and the value is something else stored in this key item pair, stored at this location of this array. So for example, for K2, if we use a hash function, if the hash function map K2 into 0, then we store K2 and plus its corresponding value at this location of the array, right? So because when we save, now we only talk about the save, how to save the key item pair in the array, or we call it hash table. See, we only do a very simple, use a function, very simple function to work out the address. So once we know the address, as you know, for array, we can directly access the element by index, by location. So we can immediately to save the corresponding key item pairs at that location. All right? So that's basically the big O for n, right? So the time is the time we spend on calculating the address, which is a constant, right? So it doesn't matter if the table, if the array is very huge or is very small, we use the same amount of time. We need the same amount of time to work out the address for storing the corresponding key item pair, right? There's a nearly big O of 1 constant time. Then how do we, for example, later on, if we want to remove, how to do that? We use the same idea. For example, if we want to remove the corresponding k atom pair for K2, so we use the same hash function. We use the same function. Given a k, we work out the corresponding address, which is 0. I know I need to remove this one. So all I need to do is to remove the k atom pair stored at this location, at location 0. All right? And searching, we use a similar idea. If you want to looking for, K2, so for example, given our address number, which is a K2, we want to find that driver's contact. Okay, so we use a K2, we use a hash function to work out the corresponding key value pair stored at the location where the corresponding the driver's license record is stored in the array, and then we get once we found an element, we can extract the information about the driver's phone number from there, from the corresponding driver's record, right? So this is the idea. So this is the key. This is the key idea. So the key idea, we need to design a hash function, right? Hash. So how hash is implemented? We use a hash function. So hash function basically is a formula that can map the key into the address of an array in which the k atom pairs are stored, right? So this is a hash function. So hash function is extremely important when you use a hash table, right? So which I'll talk about why it's very important. What's the potential problem? So what is considered as a good hash function, which is considered as a bad hash function. And for the same applications, if you have two developers to do the same workout, to do the same job, they work. Both of them use a hash table. So one guy work out one hash function, another guy work out another hash function. How would we know which one is better than other, right? So we'll talk about that next. So in the hash function, basically there are a number of popular hash functions, right? Or I should say there are different number of popular ways to define a hash function, right? And today I'm only to, for example, have division method, have multiplication method, we have middle square method, folding method, and select digit method, and so on and so forth. But because of time limitation, today I only introduce the first two. Okay. Now, before introduce the first two categories of hash function, so I would like to give you the criteria. So what are the characteristics of a good hash function? Which is good, which is bad? If you have two developers have two different hash functions, how would you know which one is better than other, right? So this is the characteristics. So a good hash function should minimize the possibility of collision. What's meant by collision? So one problem when you use hash table is we call it collision. What do you mean by collision? You may have two different Ks, for example, K1 and K2. If you use hash function, they may map into the same address. This is what we call a collision, right? So one issue that we have to deal with when you use hash table is collision resolution. So if there are a collision occurring, then how would you resolve the collision? So we have two atom pairs mapping into the same address in the array. How would you resolve the problem? All right. Of course, we'll talk about collision resolution later on, but now we look at the characteristics of a good hash function. So a good hash function should minimize. Fundamentally, sometimes we cannot avoid collision. Collision, most of the cases, they will happen. We cannot avoid. It's very challenging, to avoid collisions. So the problem is how could we minimize the collision, right? So if we have two functions, hash functions, one have a result more collision than other, then we say, of course, the second one is better, right? So this is one characteristic of the good hash function. Another characteristic is a hash function. A good hash function should distribute the key, evenly into the whole array. So you don't want to say, for example, we've got a number of key value pairs. We have a function only map those keys to the, for example, the first half of the array, where this, of course, is an extreme example, where don't map any key to the second half of the array, the bottom half of the array. This, of course, is not very good, right? Right. So ideally, all the keys should be mapped into address with which are distributed evenly in the array. Map all the possibility, all the address, distributed very evenly. So this is another characteristics. And the third one is sometimes you probably can work out a very sophisticated hash function. This can, number one, can minimize the collision. Number two, and we can guarantee all the keys are distributed evenly in the array address space. But take a lot of time, take a longer time. Then this is not good either. Why? What's the point of doing that? If we use a binary search, that's log n. Let's say if we work out a hash function whose computational complexity is big O for n, or linear search. So what's the point for you doing that? Because for example, insertion, first of all, you need to calculate the value of the hash function, which take a big O for n time, take a very, very long time. Then what's the point for using that? Then we would not have any advantages of a hash table at all, right? So the hash function should be easy to compute. Right. So when we say easy compute, I mean the computation compute ideally is a big O of 1 or constant time. Right. So this is the characteristics of a good hash function. Okay. As I said, I will introduce two categories of hash function. So this is problem dependent, right? So when you got an application where you think you should use hash table, then it's your responsibility to design a hash function. All right? So one kind of way to construct or design a hash function is called division. All right? So division, the idea is pretty simple. The idea is, for example, we have a key, and basically this is the hash function. This is the key. Given a key, this is a modular operation. So if we, in C++, this is the general one. In C++, you can read this one. This is a modular operation. Key, modular operation. This is a modular operation. Right? So this is just to show you the idea. But in the real world, when you actually use this one, sometimes probably it's not that easy. Right? But anyway, it's just to give you a rough idea. So there is practical questions about this. Now I just simply draw a diagram for just to quickly explain this. For example, this is my hash table, or this actually is an array. Maybe I start from maybe 0, 1, whatever. And this is my capacity, the size of the array. This size of array. Just example, for example, I use m-1 altogether m. But this one typically should not be the size of the array, which I will talk about why in a minute. So sometimes you can use the size of the array. Sometimes you may not use this array. So for example, let's say, just to make it a little bit easier, for example, if the size of this hash table is 11, all right? Now the k is 1. So the value is, this a modular operation, is 1, right? So we have a k is 1, and the value is something which you don't care somewhere. So this k item pair, so maybe I put item here. This k item pair should be stored at the location here, 1. So this is 1, item 1. So this is for this one. Next time, for example, if we have another one, let's say 13, the k is 13. So we use this hash function to work out the address for this item, k13, and item, for example, item 2. And the value is this modular operation. Modular operation. There is 2, right? Modular operation, the reminder. Okay. So we store this one, 13, this item 2. All right? Just one more. For example, if we have another key item pair where the key is 5, item is item 3. The 5 modular 11, still 5. So somewhere here, there's a 5. Right? So I put 5 as a key item 3 here. So like this. So in this way, we can quickly say we only spend a constant time. So whenever we insert one item pair, the time we spend basically in 2 parts. Number 1, the time we spend calculating this calculation, which is a very quick, constant time. Right? This has nothing to do with the size of the program. All right? So I probably use another one just to distinguish you to configure. For example, this is what we call P, where this is the size is M. All right? M is the size of the hash table. P just another number, or maybe a primary number, which I'll talk about in a minute. Right? So this has nothing to do with the size of the hash table. All right? So insertion very quick. Right? We work out the address and immediately save the key item pair at the data address given by the hash value. So as easy as that. Constant time. All right? So when we do search, we use the same idea for later on. For example, if we have already saved all the key item pairs, like a driver's license record, right? Driver's license number plus some other information in the array, now we need to do a search. We use the same idea. So for example, now the given key, the driver's license number is 5. The given key is 5. Where I can find the item, the information in the item, right? Where I can find the item, that's too easy. I use the same one. So 5 modular 11 gives us 5. So I can immediately find this element in this array. So once I found the element in the array, then I get the item. For example, contact phone number. Right? So very easy. So also constant time for this particular instance. Right? So this is the only time we use 2 parts. One is the calculation, another is to access this one, which is also constant time. Right? So deletion, the similar idea. If I delete that one, so use that one, calculate the address, and then you can remove the corresponding element out of the array. So this is deletion, all constant time, say. So this is the basic idea, right? Okay, so one category of hash function called division method. So that's the division method. That is one instance of the division method. This is the one way you can consider when you design a hash function. Okay, if you use a division method, there are something that you need to pay a little bit attention to. One is, for example, so we actually, if we use this function, hash function, then we should replace M with P. All right, so this is a P. So if we use this one, P here, this is P. P typically is a primary number. So our prime number is a number which can only divided by itself and 1, right? Like 11, right? So like 13 or something like that, it's a prime number, right? So you know that. Why is a bad idea to use an even number for p, for example? If an even number, then you will know the k, if the k are all the k are integers. For integer, for example, for even k, they map to the even address. For order k, map into the order address. So what happens in one application where all the k's are even numbers, right? They will map the address to all the even all the even address in the array, and the odd address will never be used, right? So they are not evenly distribute the k across the array. So this is not a good idea. Another one is there are some temptation. They want to use a p. I'm sorry, p here as a power of 2. For example, 1 is 16 because it's easy to compute, right? Or 32, right? So this is a 2 to the power of something, right? This is not a good idea. This is not a good idea either. Why? If we use 2 to the power of n, I'm not sure if you guys can follow me or not. So if we translate, so if, for example, if for this p, for the case, if we represent the k in a binary way, in a 0, 1, 1, 0, in a binary way, then you will see, for example, let's say n equals, let's say 2 to the power of n in general, okay? So if p equals to 2 to the power of n, then for all the k's, you have number of k's, for all the k's, whose last n digits in the corresponding binary representation are the same, they will map into the same address. So you can, if you're interested, you can do that. You translated the number you represent the k in a binary way, and you look at for all the k's which have the last n digits, binary digits, the hash function will map into the same address, which is not very good, right? This means they will have collisions, number of collisions. So this is not a good idea either. So what we do is we choose a prime number, right? So a prime number. So for p, it's a prime number, right? That's a good idea. If you use a prime number, then the k can be evenly distributed in the address space of the hash table or the array. All right. So this is about division. Just very quickly, talk about another categories of hash function before take a short break. Another one is we call the multiplication. There are a number of variant for multiplication method. And this is just one of many, just an example, just one instance of that. So this is h is a hash function, and x is a k. Okay, x is a k. And this is the hash function. So this is how to interpret this. So basically, here m is the size of the array or size of the hash table. And that part, this item here, the whole item here, basically, as you can see, a is a constant between 0 and 1. Okay, so we use a, that constant. Typically, we can choose this one. We just use some experience, right? So this is just an experience. So somebody found if we use this one as the constant, the work is pretty good, right? So actually, this one discovered by that guy over there, right? So we use this constant times the k minus the constant times the k, but this time, So this part is an integer. So this is an integer. So which means we round down. So if there are any division in decimal part, we just get rid of the division part. So this part minus that part actually is the fractional part of this, right? Understand? Yeah. Maybe I use an example. So let's say, just an example. Let's say currently A equals to 0.5, all right? And M equals to 10. This is the size of the hash table. This is the maximum number of key item pair that we can store in hash table. This is the size of the hash table. And now if the K is X, K, let's say, is 5, all right? So now M times the first part is A times X and minus this integer operation A times X, right? So this part, this is 10 times A 0.5 times 5 minus integer operation 5 times 5. This 2.5, right? Round down, that's a 2. This is 2.5, 2. This is 0.5. So 0.5 times 10 gives 5. Of course, integer operation. So the address would be here, 5. All right? So this is just an example. Okay? This is another category of hash function, right? So we can use it to function. But no matter which hash function you use, there's one problem that it's very hard, and generally speaking, you cannot avoid, which is, I said earlier, is collision. So you cannot avoid, for no matter which function you use, you can probably map two different key into the same address in the hash table. All right? So let's take a 10 minutes break. So when we come back, we'll talk about how to resolve the collision in hash table. Now, let's talk about how to deal with collision in hash table. Right? Hash table, one problem, as I said before the break, there are one problem that in most cases we cannot avoid is called collision. So just to give you an example. So for example, this key item pair 1 item 1 map into 1. So if I have another key, let's say the key is 12, this item 4, right? So 12 modular operation, that's also give 1. That's indicate this also map into this location. But the problem is this key item pair has already occupied that position. Now we have a second key item pair, which also map into the same location. So this is a collision. So collision occurred, right? So for this problem, so how would we resolve collision, right? So again, collision is a situation where we have two key item pairs, and the key map into the same location in the hash table. This is what we call collision. So there are two strategies or two categories of strategies for solving collision problem. One is called open addressing. Another one is called separate chaining. Open addressing, the basic idea is to search the array in a systematic way to find the empty cell. Okay, starting from, for example, here we got a collision, but now this is already occupied, used by another key and pair. So starting from here, starting from the collision site, this is called a collision site. collision location or collision site. Starting from here, we use a systematic way somehow to find the empty cell. For example, here or maybe there, depending on which strategy you used. And then we put the key item pair at another empty cell. Right? This is the first category. The second category called separate chaining. Separate chaining means actually we use an array of linked lists. Okay, I'm talking about the detail to store all the key item pairs that map into the same address. I explain to you. I'll use an example later on. Now we look at open addressing. The first category, open addressing. Open addressing, there are three most popular ways, right? The first one is very simple. It's called linear probing. So what's mean by linear probing? So we're talking about one by one. Linear probing, I probably use this example. So for this one, now this one is coming. Now this one has arrived. This key item arrived. Now we need to insert this key item pair into the hash table, into the array, all right, which is our array. So when we calculated the hash function is also 1, but 1 has been occupied, all right? So how we found another empty cell, find an empty cell where we can store this new key item pair. If we go with this option called linear probing, so linear probing, very idea is pretty simple. This we call the collision site, maybe for example location H. Okay, this is hash value H in general. Then we check the next section, next location H plus 1, which is this. But this one is also occupied. Then we further check the linear, like a linear search, right? H plus 2, this is empty, all right? Because it's empty, we put here 12 item 4 at this location instead. This is about insertion, right? So you probably ask me, then what about, for example, search? So later on, now this one has already been included in the hash table. Later on, for example, given a key which is 12, how could we find the corresponding key item pair? Use the same idea. So first of all, you calculate the address. The address is 1. Then you need to do comparison to say if this key is 1, the key item pair stored at this location is the key item pair is 12 a lot, but this is 1. Does not match up. So you have to, if we are sure we use linear probing, then you need to check the next one to say if this 12, no, 12, yes, then you return the corresponding item probably. All right? If we use a linear probing. All right? So, of course, there are some other issues. For example, when should you stop the search? All right? When you can stop the search. So you stop the search until, we're talking about the search, not the insertion anymore. So when you get an empty cell. Okay? So this is when you should terminate the search. This is a linear probing. So linear probing will have another concept, which I'm not mentioning here. We call it probing sequence. Right? This is called a probing sequence. So H plus 1, H plus 2, H plus 3, H plus 4. So this is the probing sequence used by linear probing. Right? So this is one systematic way. Another method, so one problem was, I should mention to you is we call one problem with linear probing is called primary clustering. So what's meant by primary clustering? So for example, if we have another key item pair, for example, the key is 23. It's item 5. If you use this one, so 23 modulo operation 11 also gives 1, right? also give 1. So which means there are another collision, also map to this location. Now, if we want to insert in this case to this hash table, we need to do the same. We use the same probing sequence. We also start from here, not empty, not empty, not empty. This is empty. So we put this one, 23, item 5 here. Right? So put it over there. So as you can see, for all the keys that are mapped into the same address, they are clustered in this area. So starting from this position, maybe cluster into this area. They never jump put some other area. They always follow in that one, you cluster into. This we call a clustering problem, right? So maybe if clustering, if there are a lot of keys which are mapping into the same location like this in this hash table, then you will see all the key items are stored, clustered in some area. Where in some other area there's no key item pairs at all. So this is not very good, not evenly distributed, right? In this hash table, this is not good. So this is a problem. So one solution to the problem is this is actually another open aggressive method. That's called quadratic probing. So which mean by quadratic probing? Quadratic means also it's a systematic way to search for empty cell in hash table to store a new item pair. But this one, instead of use, so if we use a linear probing, so the probing sequence is H plus 1, H plus 2, H plus 3. If we use quadratic probing, then this search sequence, the probing sequence, would be starting from this location in general H. So if this is a collision site, H has been probably already occupied by another key item pair. The next one is you need to explore to see if it's an empty cell or not. You need to check is H plus 1 square, which is still plus 1, right? And the next one you should check is 2 square, H plus 2 square, which is H plus 4. And then 3 square, which is H plus 9, and so on and so forth. So while we're doing that, so for example, if we got just example collision here, now we need to find our address. So the first one we check is H plus 1, which is this. H plus 1 is also occupied. Then H plus 4, 1, 2, 3, 4, also occupied, right? Then we further check this one, H plus 9, 1, 2, 3, 4, 5, 6. They could ramp around. Okay, ramp around. If you hit the wall, they can ramp around, right, to plus 9. Okay, so like this is just an idea, right? So for this one, as you can see, there is no first clustering problem. So you can see not for all the key, just clustering in this area, right? But there's another problem, which we call a secondary clustering problem. So what do you mean by secondary clustering problem? The secondary clustering means for all the keys which have the same hash value or map into the same address, when they're looking for the location where we store those item key, we always use the same. We also use the same sequence, right? The probing sequence are the same. We always check this location. We never check other locations. All the keys map into the collision site. We always use the same. We only check those cells to see if they are empty or not, which is not very good. This is called secondary clustering. So that's why we have a third method, which we call a double probing, right? What's the motivation for double probing? Double probing means we're trying to even for let's say two different keys, even they map into the same location, But when we find a, we use a different probing sequence to find a new cell, new data cell for the two different ones, right? Rather than always use the same sequence, right? So I just use an example, probably use an example to demonstrate the idea. For double probing, as name implies, we use double probing. We use two hash functions, H1 and H2. And H1 we call the primary hash function. The primary hash function is used to start from where we started probing, okay? Where the second hash function, H2, is used to decide the steps of the probing size or probing step. Okay, I use an example to show you what's meant by double probing. So, for example, this is one double probing where we have two functions. We have H1, we have H1, we have H2. So the first function determines the starting probing address. So from where we start probing. And the second one, again, is the size, determine the size or the steps of the probing or probing size. Okay, let's say just an example. So for example, for this one, we assume this hash table only have 11 items. So hash table size is 11, right? So now, if we have a key, let's say 58. So first of all, we use the H1, hash table H1, which is this. So K modulo 11, K modulo 11 gives 3. So 3 is, for example, here. 3, for example, this is 3. This is my starting, probing starting point. When I try to find an empty cell to store a new item pair, I start from here. This is my starting point, right? And then the second function, I use the second function, which is this. I use the second function, 7 minus K modulo 7. So 7 modulo 7 minus KK, which is 58 modulo 7. This part gives 2, right? And so the result is 5. So 5 is the step. So step. So when I trying to find an empty cell in the in this hash table, so I start from this location, given by the value of H1. So this is 3. I start from 3. So the first one I check is this 3. And the next one, so this is very important. Next one, so after 3, this is the step size. Step size is 5. So step is 5. 3 plus 5 gives 8. All right? So I check this location to see location 8 is empty or not. And then if it's also occupied, then 8 plus 5 run per round because the size of the hash table is 11. So this is 2. Then we check if this location has been occupied or not. And the next one, 2 plus 5 gives 7, and so on and so forth. Okay, until I find an empty cell in the hash table. Right. So this is another one. So for this one, this does not suffer from any clustering problem. There's no Foster primary cluster or secondary cluster. There's no problem, right? So actually, you just an example. If you use another one which map into the same, have the same value. For example, map into 3, but the probing sequence is different. So just example. So remember, the first hash value is 3. So initially map into this address 3. So if we have another key, let's say 14. So 14, if we use the first hash function H1, they would map into the same location, which is also 3. There's a collision, right? But this time, the probing sequence is different for different key. So why? Because we still start from here, but the step is different. Why? The step size is 7 minus 14. 14 is the k modulo 7, which is still 7 because this gave me 0. So the probing sequence would be different, as you can see. The first one, this is a collision site, right? We actually start from here. 3 plus 7 gives it 10, and then modular operation, ramp around, 6, 2, 9. So this is the different sequence. Take another look of the initial sequence. So this is the sequence for this k, 58, where this one is the k for 14. So even they map into the same location, right? But the probing sequence are different. So they don't have any clustering problem, right? So this is the third one. Any questions so far about linear, about open addressing strategy? All right? Should be pretty straightforward. Anyway, there's an exercise about this in week 8, in workshop 8. All right? Oh, there's one thing I should have mentioned before moving to the next one is when you, so how would you design, for example, there's some challenge when you design, when you choose the, for example, the size of the hash table, and also make sure, because when you're probing, one important issue is when you're probing, when you're trying to find an empty cell to store a new key item pair, you must make sure the probing sequence cover all the location in the hash table. So you don't want to say, oh, there is one location which is empty, but when you're probing, when you're looking for location following a particular probing sequence, they never come to this location. That's no good, right? So there are some there's some mathematical stuff over there, so which I can ignore. So if the greatest common divisor of the size of the hash table and the size of the probing step is 1, okay, then we can make sure the probing sequence cover all the locations in the hash table, right? So this is something that you pay attention. Of course, and another one is hash2, which determine the step size should never be 0. If it's 0, this is not a sequence. Always focus on the collision site, right? So this is something that you pay attention to. Okay, separate chaining is another category of collision resolution strategy, right? Collision separate chaining actually is very easy. In week 8 particles, actually you will use this one. Okay. You will not use open addressing. Actually, you will use this one. This is the one that I use in the particle questions, right? So basically, as you can see, we have an array. So this is a hash table. So for each hash table, store are basically is a pointer. Is a pointer pointed. Actually, is the header of the linked list. So there's one linked list. There's another linked list. There's a third linked list. It's a linked list, right? So what do you mean by this? So if we have, for example, if you look at the top linked list over here, if we have 3 different key item pairs which map into the same location, for example, this location, I simply insert all of them in this linked list, right? So all the node, so so this is a key. This is a place where a key item pairs is stored. This is a second key item pair. This is third key item pair. All the key item pair map into the same location. So if there are collision, we put them in the linked list. Too easy. All right. Of course, you don't have to use a linked list. You can use also, for example, in the particle, actually use a vector. Okay, a vector of vectors, right? Okay, you actually use that one. A vector of a vector pointer. A vector of vectors of a record or key item pair pointer. Okay, your tutor will explain to you in more detail. So separate chaining, very quickly for separate chaining, well, sometimes it's good, sometimes it's bad. So when for example, deletion very quickly, right? So you can deletion, you can mapping into the address, and then you search for the corresponding linked list, right? To find the key item pair, and then remove the corresponding node from the linked list. Insertion, you always, if you're collision, right, it doesn't matter collision or not. Whenever you map into location, you simply insert the corresponding, insert a node in the linked list in the front, right? It doesn't matter, right? The order doesn't matter. And searching, the similar idea. Okay, now very quickly summarize the two different, or the head-to-head comparison about two different strategies: open addressing, separate chaining. So which one? So when should I use which one? Which one is better than other? So you have to say which one is better than other, right? Depends. It's program dependent. It depends. But the general idea is, when should I use a separate chaining? The general idea is, if you know the total number of roughly the total number of character pairs in advance, you should use open addressing. If you don't know, then you'd better use a separate chaining, all right? Because you don't know what's the eventually the size. For example, if you don't know the total number of character pairs in advance, you say, oh, initially I say maximum of 100, so I use a size of size of one array or hash table whose size is 100. But eventually it turns out we got 200. Then how would you do, right? So you would have to reshape, to extend the hash table, right? So this is something that you will do in in workshop 8, I should say, or particle 8. All right, so I'll quickly talk about this. And there's one issue which affects the efficiency of your operations, like a search, like insertion, deletion. There's only one factors. We call it load factor. So this we call load factor. So this, by definition, what do we mean by load factor? Load factor is the total number of key item pairs divided by the array size. Okay, array size. So how many? This we call it load factor. Okay, so this is just some experience, based on the experience working in industry, So when should we should control normally, depending on which type of resolution, collision resolution scale or strategy you use in your application. If you use open addressing, you should make sure the load factor should be between 0.5 and 0.8. This is just by some experience, And if the loading factor, for example, is too high, that's generally speaking, that means take a longer time to search an item, to insert the item, to remove an item from the hash table, right? If, let's say, if it's greater than 0.8, then if the load factor is too small, let's say less than 0.5, that indicates you waste a lot of space. Most of the space, or half of the space, more than half of the space in your hash table are not used. That's a waste, right? So, but if you use a separate chaining, this is general guideline. The load factor should be between 0, 1.0, and 1, and 2, right? So this is for the same reason. Okay, now quickly, this is something that is very important. I must cover in today's lecture. So this is the implementation. So in the practical, you will be given some implementation for hash table for a particular type of character pair. But your major job is to extend so that the hash table can use any type of character pair. So, and the technique you will use again is template. Use a templating technique to do that. Anyway, your tutor will talk about you. So now we look at the fundamental one, the basic one, which only working for a particular key item pair, where the key is a string and the item is also a string. All right. So this is the hash table that I'm talking about. So in order to do that, so basically again, for this container hash table, again is a container. There are two type there are two IDTs, right? So first of all, for k-item pair, we need a data structure to model the k-item pair, right? And of course, we have another data structure. We have another IDT to model a hash table, or another class to model the hash table. So each instance of hash table is a hash table, right? And each instance of k-item pair is a k-item pair, right? Now, but with a different different name, we call it record. So each record represents one k-item pair, right? So we use a class called record. So this is the name of the class, right? So the name of, in this class, there are two class members. One is the key, another is item. But both key and item, again, are strings. All right, so for this one. So we, of course, we need to have some mutators and accessors. For example, we need to get the key, get the item, set the key, set the item. We don't need to set the key. We need to set it. Sometimes we only allowed to change the item, but we are not allowed to change the key. So we don't have a set key, right? So this is the those are the typical member functions defined in class record. So this is a .h file, right? .h file, you can see. We look at this is the key. This is the key, which is here, string. The value, as you can see, is also string. So key item pairs, this is the place where I stored the key, and this is the place where we stored the value, right? So we have mutator constructors, of course, and also we have mutators, accessors, and also we have, what's that? Anybody can tell me? This one. Operator overloading, right? We'll overload this operator, right? So one thing I should point out that this one, as you can see, is a friend of this class, which means because this function is a class, is a friend of this class, so this function has the privilege to access the private data member. Otherwise, you can't. So only friend can do that, right? But this one is not a class member function. This is something outside. It's something like an independent function, right? Because we want to get an independent function to access the private data members in this class. So we grant friendship to that guy, to that independent function. So this is not a class member. So when you template, when you do the templating, when you template, so this way should be templated in different way. Otherwise, it wouldn't work, right? So your tutor will tell you that. There is a second class called hash table, or IDT, we call it hash table. Hash table, of course, we take a look of the data. Typically, in most of the cases, we use array. But here, just to keep it simple, we use vector, right? Use array definitely better but of course more complicated. You would have to use a dynamic array because the hash table can shrink, can extend and shrink, right? Which means you have to use a dynamic array, right? But this just, we use a vector just to make the implementation, the work a little bit easier. But probably it's not a very good idea in the real world. It's not a good idea. Why? Because fundamentally, so our vector is also implemented in the array, in the dynamic array. So what's the point, to actually introduce a level of complexity in between? So the hash table can directly use array, dynamic array. Why you use array through vector, which may not be very efficient sometimes, right? Anyway, this is just for the practice purpose, right? So these are vector of vectors. Okay, so we have a vector and vectors. So why we have vector of vectors? So this is my hash table. This is my hash table. So we use a vector instead of an array, right? This is a vector. This is my, basically we use a vector as a hash table. Because in this implementation, in this hash table, we use separate chaining. So which means we needed to store something like that, a linked list, right? But instead of using linked list in this implementation, I use another vector. This is another vector to store all the k-item pairs that map into this location. I use a second vector to store all the value mapping into this location, and so on and so forth. And each element in the vector is not a record, it's not an object of record, but it's a pointer to a record. Why? Because if you use a record, you would have to allocate all this space in the first place. But eventually, you only use a few of them. So this is the total, waste a lot. But if you use a pointer, it doesn't matter, because the pointer does not occupy only, for example, 4 bytes into this machine. It's not a big deal. It's all fine. So maybe the record is very huge. Record k item per bit very huge, right? So it doesn't matter. We only use a pointer. If we use a k-item pair, we create an object and get a pointer rather than give the the maximum space in the first place, right? So this is the idea. This is something you need to understand otherwise. And also we have some other parameter, other class members like, for example, this number of elements. That's the total number of k-item pairs currently stored in this hash table. The capacity of the hash table. There's basically the maximum number that we could store, but this can shrunk. So this capacity is actually just used to say if you reach the capacity or not, right? And this is the load factor, which is defined again total number of k-item pairs divided by the size of the hash table, right? So this is updated from time to time. Whenever you insert a k-item pair into hash table, you need to update. Whenever you remove, you also need to update as well, right? So this is the load one. Okay. This is a very important one. This is the hash function. So basically, this hash function, which I will show you in a minute, is categorized into a division method. Of course, it's a variation division. It's not that straightforward, as you will see in a minute. All right. And rehashing means, which is also a private method. For example, if we didn't know the size of total number of hash table in advance, and now we have already reached the capacity limit, then we needed to increase the size. So if this happens, we need to do rehashing, right? This is what we call rehashing, all right? So there are some, of course, constructors, destructors, which is very important because we use a dynamic memory, right? And we have a size which return the size of the hash table. We check if the hash table is empty or not. We clean up the hash table, and so on and so forth. So this is a method. Now, quickly, we look at the implementation. We look at the implementation very quickly. So this is just some highlights, which I have already covered, right? So the vector, for example, variable data is a vector of vectors of record pointer, and the size, and so on and so forth, right? Now we'll talk about the implementations. I'll probably skip this one because it's pretty easy, right? This is just create an object for the hash table, and this is the size of the hash table, and this is just an example. For example, if you want to use a hash table to store the phone number together with the information about the owner of the phone, so you can use that one. And hash function. So this is a hash function. I don't think I have much time to explain this one in detail, but I believe if you are not very clear, if you don't understand this, you can ask a tutor, right? So this is basically as I said earlier, is a sort of division hash function. But basically, they actually calculate the characters, what's the corresponding integer value for the characters, and somehow we add them up to form the hash value. So this is the basic idea. But unfortunately, I don't have too much time to talk about that. Okay, so now we look at the three most important operations defined in the hash table. The first one is insertion or insert. So for the insert, so this is insert. So giving a pointer, so for this one, when you make a call to this function, of course, you need to create an object of record where key items, you put the key, you put the item, right? Now, you call insert function to insert this key item pair pointed by this pointer into the hash table. All right? So the first thing we do is this is a hash function. So this is a hash function. Get hash is a hash function. So this returns the address in the hash table. Okay, we put the address or the location into index, and then we simply, because we use a vector, it's very easy. We simply push. Push which one? Push what? Push this record. Actually, the pointer to that record into what? Into the corresponding vectors. So we have vector, and we have a number of vectors, one vector, second vector. For example, if the location here, we push the corresponding, we push the pointer to the key item pair into this vector. Push back. Okay? So this is the 8. So after that, we increase the number by 1, total number increased by 1 because we got a new one. And also we need to update load factor, right? Load factor. And if it's, load factor is exceeded to the next one, we need to rehash. We need to increase the size, right? For search, we call it find here. We use the similar idea. So first of all, we use a hash function to find the location, and then we need to find the corresponding key. For example, if this is the corresponding vector, in this vector, we need to find that could be multiple, quite a few key and item pairs or records pointer, right? So we need to find the one we are looking for by using the key to say if the key match up. So this here we have to use an iterator, but no, we don't. So this is not quite right. So you can use an iterator to go through the element in the vector. Alternatively, you can treat it as an array. You can use, index from 0 to array vector size. Probably, if you're more comfortable, if you use that one, that's perfectly fine, because vector can also treat it as an array, right? So this is the erase. So you find out, given a key, you find the corresponding location, and you find the corresponding vectors, and you get rid of the record from, actually the pointer to the record from this vector, the corresponding vector, right? The idea pretty much is the same. And this rehash, how to increase the size, increase the size. So if we have already reached the limit capacity, so we create another array which has a bigger size, okay? And then we need to copy all the key item pair initially. We store it in that vector into the new vector, which is bigger, right? So this is the basic idea. All right, and also there are, this also you need to do in workshop 8. So we added some other functions, like you need to count the total number of records, you need to count the total number of collisions, and also you need to find the largest bucket, right? So you tutor will talk about that. All right, so this I think this should be probably leave this one to you. So hash function again is a very efficient data structure. It's because for insertion, deletion, and search, they only take a big O for n times, which is very efficient, right? So I'll leave this one to you anyway. This is pretty straightforward. So the key is hash table can only use in key item pairs collections, all right? Okay, thank you. See you next week.